The problem states the 1.5 megagram four-wheel drive Jeep is used to push the two identical crates, each having a mass of 500 kilograms. If the coefficient of static friction between the tires and the ground is 0.6, determine the maximum possible speed the Jeep can achieve in 5 seconds without causing the tires to slip. So our period is 5 seconds. The coefficient of friction between the crates and the ground is this is kinetic friction, is 0.3. So let's look at this problem. What it's saying basically is the Jeep moves this way, the crates slide, however, the tires do not lose grip. So we're looking at static friction for the tires and kinetic friction for the crate and the ground. So as a part of the problem, this is not given, but I got this equation from the textbook because it will be helpful for solving this problem. So first, we start off with a free body diagram because we want to know what sort of forces are happening on the Jeep and also on the crates. So if this is our Jeep, we'll make it look a little simple. We have the following forces. We have the normal force, which is equivalent to the weight of the Jeep. So this is the weight, which is 1.5 megagrams times G. And we have the normal force, which is, I'll call that NJ. And we have friction pushing the Jeep in this direction. So this will be friction, and we'll call this mu sub s times n sub j. And we also have the force that the crate applies on the Jeep. So it's that force, and that will be equivalent to, let's say, P. So that is the diagram for the Jeep. Now let's draw the diagram for the crates. So we have the two crates here. Let me actually move this stuff around. So we have the weight of the crates, and there are two of them, each weighing 500, so that's 1,000 kilograms times G, which is actually due to gravity. We have the normal force for those crates, which is equivalent to, let's say, NC. We have friction, which is going in this direction because the friction is opposing the travel. So we get, let's say this is, so we have kinetic friction, so that means N sub C times mu sub K. So that is our friction. And then we have the P, which is the force that the crate exerts on the Jeep, and that is pointed in this direction. And we'll call this P. All right, so that concludes the free body diagram. Let's not forget the X and Y axes because it's important to define. So that's X, Y, and X, Y. Perfect. So let's first apply this equation for the Jeep. So this impulse momentum equation, we'll first apply it in the Y direction. The Y direction. And we have mv1, which is our mass times initial velocity. And we know that the velocity in the Y direction is 0. So we'll call that mj times 0 plus we have this term, and this may look like, oh, we have an integral, is this hard? But what this basically is saying, like, we have the range t1 to t2 integrated f dot dt. So that basically means we have the constant force applied, which is, well, if the force is constant, then it becomes simple. Otherwise, you actually do have to integrate. But since we have constant force applied, you can think of this term as F times T, because our F is constant. So what are our constant forces in the Y direction? Well, we have the N sub J applying over 5 seconds, and that is in the positive direction, so that's a positive term. And we have 1.5 megagrams times G, and we'll just call that W, and that is pointing in the negative direction, equals m times v2. And again, the movement is completely horizontal, so our final velocity is also 0, and this becomes the mass of the Jeep times 0. Let me just move this stuff around really quick to make some space. So we can go ahead and solve this really quick. So this will become n sub j times 5 equals W, and we know that W is literally just the weight. So we have 1,500 kilograms, which is equivalent to 1.5 megagrams, times G, which is 9.81. And when we solve this for n sub j, we get that equivalent to 14,715 newtons. So now let's solve this in the x direction. And this will be similar. So we have the m times v1, which is the mass of the Jeep, times the initial velocity. And in the problem, it says that the initial velocity is 0 because we're starting at rest. So let's solve this. So we have the mass of the Jeep, which is 1,500, times our initial velocity, which is 0, plus we have, let's see, what forces do we have? We have the P pointing in the negative direction and static friction times n sub j. So in the negative direction, let's do the n sub j times static friction. So the coefficient of static friction is 0.6 times we have the n sub j, which is 14,715, times the total time, which is 5. Then we have P pointing in the negative direction times, again, 5 seconds, equivalent to the mass of the Jeep times the final velocity, which is, we'll call that V for now. So solving this, we get V equals 2943 minus 3.33 10 to the negative 3 times P. So what we have right now is an expression for final velocity in terms of P. So that pretty much concludes the impulse momentum solution for the Jeep. So now let's do the same for the crate. So now we're beginning the crate with the y direction. And let's see, our mass is 1,000 kilograms, and our initial velocity in the y direction is 0, as well as our final velocity. So we can say 1,000 times 0 plus something 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 is going to be 1,000 times 0. And let's see what those are. So we're again looking at the term with the force times distance, force times time, and we have the force P and also the force due to friction. So P is pointing in the positive x direction, so we'll say P times 5. Ooh, sorry, I was looking at the horizontal. This is supposed to be the y direction. So we have the weight, and we also have the normal force. So let's put that in. The normal force is pointing up, so we have n sub c minus 1,000 times 9.81 times 5. Ooh, forgot to multiply. Okay, there you go. So that's going to be n sub c times 5 minus this term equals that. So solving this, we simply get n sub c is equivalent to 9,810 newtons. So now that we have the normal force, we can solve the x direction. So x direction is going to be the same equation applied, but this time in the x direction. So we know we start from rest, so we have 1,000 times 0, and let's look at the forces involved. So we have, I previously mentioned this, P and friction. So P pointing in the positive x direction, which is going to be P times 5 minus, we have the coefficient of kinetic friction, which the problem states as 0.3. So that's going to be 0.3 times, let's see, our normal force, which is this value, so 9, there you go. And this will be equivalent to the mass times the final velocity. Now, it is important to note that this final velocity value is important because notice how in the problem it states that these two move together because the Jeep is pushing the crates. So if the Jeep has a final velocity of v, this means that the crates are also going to have a final velocity of v. And then this can give us an expression for v in terms of p, similar to how we have that for the Jeep. So now let's find that expression by doing some algebra. And we get v equals 0.005 p minus 14.715. So now I'm going to grab these two equations. So we get from the top here, we get this one. And we also have this equation here. So note that these equations are two unknowns and two equations. We have v, v, and p, and p. Using basic algebra, we simply solve this as 11.8 meters per second for v, and we do that by isolating p and setting the equations equal to each other. And that concludes the answer because, again, the question was, what is the maximum velocity that can be reached? And we know that these particular coefficient of friction values give us the maximum the maximum velocity. And this is the value, and that concludes the solution to this question.